In this tutorial, we will work through an example of how to find the rate law and rate constant from initial rates data. The rate law gives the relationship between the reaction rate and the concentrations of reacting species. For a reaction between A and B to form products, the rate law would have the general form of rate equals K times the concentration of A raised to the power X and the concentration of B raised to some unknown power Y. K is called the rate constant in the reaction, and the exponents x and y are the orders of the reaction with respect to reactants A and B respectively. Remember that all rate laws must be determined by experiment. How do we use the method of initial rates to determine the rate law? First, you need to measure the initial rate of a reaction when the concentrations of the reacting species are known. Then you change the initial concentrations of just one of the reactants while holding everything else constant, and measure the new rate of the reaction. Step 3. Use the above data to solve for x in the following rate law equation. You'll need to repeat this process for each reactant. Let's use the method of initial rates to solve this problem. Use the experimental data in the table below to determine the rate law for the reaction A plus 2B goes to C, and determine also the value of the rate constant. The table above shows the initial concentrations of each reactant for the 3 experiments performed, as well as the experimentally measured initial rates. First, we'll need to find a pair of experiments for which one of the concentrations doesn't change. Let's start with experiments 1 and 2. In these experiments, the concentration of reactant A is a constant at 0.02 molar. However, the concentration of reactant B is increased by a factor of 3 from 0.1 molar to 0.3 molar. So again, we're going to start this process by looking at experiments 1 and 2, for which the concentration of A was held constant at 0.02 molar. From experiment 1 to experiment 2, the concentration of B was increased from 0.1 molar to 0.3 molar, which is a factor of 3. What happened to the initial rate of the reaction when we increased the concentration of B? For these two experiments, we see that there is no change in the initial rate, even though we have tripled the concentration of B. This means that the reaction must be zero order with respect to B, because concentration of B to power Y doesn't change the rate, just multiplies it by 1. That means Y must have a value of 0. On the other hand, what happens when we look at experiments 2 and 3? In this case, the concentration of B is held constant at 0.3 molar, but the concentration of A is tripled from 0.02 to 0.06 molar. When we triple the concentration of reactant A, we see a 9-fold increase in the rate of the reaction. So tripling the concentration of A increases the rate by a factor of 9. 9 has the value of 3 squared, meaning that this reaction is second order in the reactant A. We can now write the rate law for this reaction. The rate will be equal to the rate constant K times the concentration of A squared, because A is second order. Notice that concentration B does not appear in the expression for the rate law because the reaction is zero order with respect to reactant B. Next, we want to use this expression to solve for the rate constant K. We can take the rate law and solve it for K. In this case, K will be equal to the rate divided by the concentration of A squared. We can choose any of the above experiments to determine the rate constant K. Let's use experiment 2. For this experiment, The initial rate is given as 0.057 molar per minute, and the concentration of A is 0.2 molar. Notice that we have to square this concentration, again because of the rate law. Plugging these numbers in gives 140 per molar per minute for the value of the rate constant K. Notice the units for the rate constant vary depending on the overall order of the reaction. In this tutorial, we work through an example of how to find the rate law and rate constant from initial rates data by assessing the effect of changing concentrations on the rate. In this example, the reaction orders were able to be determined by inspection. For more complicated examples, logs can be used to find the values of the exponents. The following video shows an example like this.